So previously, we practiced converting polar coordinates to rectangular coordinates and the other way around. Now we're going to try our hand at actually converting polar equations. So all this means is typically polar equations are functions where r is a function of theta, meaning our directed distance depends in some way on what theta is doing. And what we're going to try to do is take a polar equation, which is r as a function of theta, and rewrite it into some equation that involves just x and y. In other words, we're going to try to find a way to change r and theta, our equation in terms of r and theta, into an equation in terms of x and y. I've already gone ahead and written out some of the equations and formulas that we have used in the previous part of the lesson to convert polar coordinates to rectangular ones, and I'm going to leave those up there. But let's try our hand actually converting some of these polar equations. So, starting with this first polar equation, it's a very simple one. R is just simply equal to 5. We can see here that R is always just going to be equal to 5. So, how would I go ahead and change something like this? Well, look back to our equations here and ask yourself, is there anything here that I can use that changes something that I have in terms of r to that of x and y? And you'd want to be looking at this one right over here, right? R squared is equal to x squared plus y squared. So let's go back to our equation. And if we know that r is equal to 5, we can say that since r is equal to 5 and r is equal to x squared plus y squared, we can very just simply say that r is equal to the square root of that, I should say. R is equal to the square root of x squared plus y squared. And since we know that r is equal to 5, that is our rectangular equation. It's that simple. There's really all there is to that. We know r is equal to the square root of x squared plus y squared. We're told that r is equal to 5, and that's pretty much it. However, as soon as we get ourselves into a rectangular equation, we want to look at our rectangular equation and ask ourselves, do we recognize what type of graph we might be looking at here? And if so, we want to make sure that we write our equation in its standard form. So take a look at that there. If we can see very easily by just squaring both sides, that we end up with x squared plus y squared, and the square root is negated, and we're left with either 25 or 5 squared. And ask yourself, what type of graph would we get here? And this would indeed be a circle. Now, pause and think about our graph here for a moment. Think about what the graph of r is equal to 5 would actually look like. And to aid you with that, let me go ahead and just place this over here and make that a little bit larger. And ask yourself, what would the graph of r is equal to 5 actually look like? Well, what we're saying here when r is equal to 5 is that regardless of our angle, our distance from the pole is always going to be equal to 5. And if I just went ahead and just quickly labeled this here, 3, 5, our distance from the pole is always going to be 5, no matter what our angle is. In other words, we would get something that looks just like this. And this is a pretty large circle there, but you get the idea. Our directed distance is always going to be r is equal to 5. And what would the graph of x squared plus y squared be? It would be a circle. That's exactly what we have there. So hopefully that kind of connects a little bit of why that polar equation gives us the same graph as that of the rectangular equation. It's because they are the same equation. They're just in different forms. All right, let's try another one. We got theta is equal to pi over 4 now. Now, again, go back to these equations here and ask yourself, do I have anything that converts theta into something in terms of x and y? And we do. We can use tangent of theta is equal to y over x. So we can say here that tangent of theta is equal to y over x. That means tangent of, in this case, what is theta? What's given to us? Theta is equal to pi over 4, and that's equal to y over x. Well, we know what tangent of pi over 4 is. That's simply 1. So we can say y is simply equal to x. And let me take a moment here just to again, reiterate, why exactly would theta equals pi over 4 be the same exact equation, or same exact graph, give us the same graph as y equals x? Well, again, if I were to go ahead and graph that here real quick. So again, 1, 2, 3, 4, 5, 6. Ask yourself, what would theta is equal to pi over 4? What would that graph look like? What we're saying here is that no matter what our directed distance is, our angle is always going to be equal to pi over 4. What graph do we have? Exactly of that right over here, y equals x. So hopefully that makes a little bit more sense there. Now, this next one is a little bit trickier than the previous two, but still not too bad. So take a moment and pause the video and ask yourself, how would I take this equation, that's a polar equation, and rewrite it into an equation in terms of just x and y? Well, there are a couple ways you might have done this, but the first thing that I'm going to do is I'm just going to multiply both sides by the denominator. So write this as r 2 cosine theta plus sine theta. Make that equal to 5. And then I'm going to distribute that r now, and so I would get 2r cosine theta plus r sine theta. Make that equal to 5. And take a look at what we have here. We have r cosine of theta. And if we go back to our equations, we know that r cosine theta is equal to x. And r sine theta is equal to y. Well, using those, let's go back. So if we know that 2r cosine theta, we can write that as 2x. R sine theta is simply equal to y. And if that's equal to 5, what do we have here? We have 2x plus y is equal to 5, which, ask yourself, what type of graph would we get here? You're right, we would get exactly that of a line. So there's our solution there. So take a moment, pause the video, and try these polar equations and see if you can convert them into rectangular form. All right, let's try to go through these. So looking at this first one, like we did in the previous problem, I'm going to multiply both sides by the denominator. So r minus r sine theta is equal to 3. And I'm going to now start substituting what I know. I know I can rewrite r as square root of x squared plus y squared. And r sine theta, I know all of that is equal to y. And from here, I have a square root. I have a radical. So just like we did earlier in the year, I'm going to go ahead and move that y term over to the other side. So that way I can square both sides. And that what leaves me with is x squared plus y squared is equal to y squared plus 6y plus 9. And if I go ahead and just start simplifying here, subtracting y squared from both sides, I'm left with x squared is equal to 6y plus 9. And ask yourself, what type of graph would we get here if one term, specifically the x, is squared? And you're right, we would get a parabola. So since we have a parabola, let's write it in the standard form for a parabola. Just to review what that is, x squared is equal to 6. We're going to factor that out. Y plus 3/2. And if you're a little sketchy on your memory, go ahead and review the standard forms for all of your conic sections, because that there is indeed a parabola. Okay, let's increase the thickness of the pen real quick. All right, now this next one. Here, we're going to go ahead and rewrite this as 2 over cosine theta. And if you're seeing this equation now as r is equal to 2 over cosine theta, hopefully that now kind of jumps out to you a little bit more what we have. We have r cosine theta is equal to 2, which means we can write all of this as just being equivalent to x. So x is equal to 2, and that makes sense. That's just a vertical line. All right, now this next one here, we have theta. And just like we did in the previous problem, we're going to use tangent. We can say that tangent of theta is equal to y over x, and we're given theta, so tangent of 11 pi over 6 is equal to y over x, which that evaluated would just be negative root 3 over 3. So then y is simply equal to negative root 3 over 3 x. And this, again, gives us just a line with a slope of negative root 3 over 3. Now the last one in this section, just like we've been doing in the previous ones, we're going to rewrite this as r plus r cosine theta. All I'm doing is multiplying both sides by the denominator. And like I did before, I'm going to go ahead and substitute now what we can for any of these terms. We know r is equal to root x squared plus y squared. R cosine theta is simply equal to x. And now we're seeing a pretty similar problem to the first practice problem we just did. We're going to write this as root x squared plus y squared is equal to 2 minus x. And so that I can negate that radical, I'm going to square both sides. And that would give me 4 minus 4x plus x squared. Got my negatives right? Yes. And y squared then is equal to 4 minus 4x, because you can see that these x squares would be negated once we subtracted both sides by the x squared. And just like we saw before, now we have a parabola, which, so we want to write that in its standard form. And if you just want to review your conic sections, you can ask yourself, all right, so then what would I know about my p-value? Which way would my parabola be opening? So hopefully that helped in terms of giving you a little bit of practice of working with converting polar equations to rectangular equations using any one of these key formulas to really just think about how can I express an equation with r or theta or both and write them in terms of just x and y.